quick start so that we can jump in and get started with the logic functions, truth tables, and Boolean algebra. So we're just going to touch on the basics of these. My goal is that I like to jump in and get to where we can actually do things with digital logic. And so I don't want to spend a lot of time developing every concept because a lot of these things I think are relatively obvious once you see the trick. All right, so let's get started. First of all, let's talk about logic functions. Okay, so we're going to be looking at gates. One gate would be an AND gate. There's also an inverter gate. So maybe if I put in input X, I get an output function F. Here I put X and Y, I get an output function F. And then the one we're going to talk about today is OR. All right, so we're just going to talk about these three in this video. All right, so one of the things you can do to specify the logic function is to realize that with digital logic, because it's basically built on transistors and transistors switch between on and off, we basically have two values, 0 and 1. All right, I think you probably knew that. All right, and so you can come up with a truth table where you just list all the combinations of zeros and ones for a given function. So for the inverter, all right, so there's an input X and an output F. There's only two possibilities for X, 0 and 1. And then the inverter just flips the bit, all right? What was a 0 becomes a 1. What was a 1 becomes a 0. So there's a truth table. Write that down, truth table for the inversion logic function. Okay, we can do a similar thing for the AND function. All right, typically we use Boolean algebra, and the way we would write the AND function is X ANDed with Y. So we can use the implied dot, or sometimes people will actually put an ampersand, or sometimes we'll just do the implied and where there's no operator that's shown, just like we did with multiplication with regular algebra. Okay, so we would have inputs X and Y and an output F. We can write down all the combinations of X and Y, and we know what AND should do. You have to have both things be true. That's this case. Otherwise, the output is a 0. All right, so notice I've been talking about true and false corresponding to 0 and 1. All right, so that's a natural thing to do with logic functions. All right, so that's the AND logic function, and we can do a similar thing with OR. Write down the input combinations and the output F with an OR. If you have either X or Y being a 1, the output is a 1. So the only place that's not true is with 0, 0. So everywhere else, this is a 1. All right, so that's a quick start. I think these things are relatively obvious, but nothing's obvious till it becomes obvious to you. All right, so play around with this if it's not something that naturally resonates with you. So the next thing I want to do is talk about a more complicated logic expression. So something like F is equal to A bar C or B C bar. All right, so notice I have this set up to look like regular algebra. So I have, the implied and here, and then the plus symbol is denoting the OR. And I have parentheses around one of the, you can see where the parentheses are. So that expresses a logic term. All right, so Boolean algebra is not the same as regular algebra because the variables only take on two different values. But a lot of the properties are the same for Boolean algebra. So the hierarchy of operations is similar. There's not a complement in regular algebra, but that's the first thing we do. We take all complements are first, then we do parentheses, and then it's just like before, you do and then you do or. All right, so there's an order of operation. So what we would be able to do is we'd be able to make a truth table for this logic function f. All right, I'm going to put the variable names here. All right, I'm going to go with ABC in that order. 0, 0, 0, 0, 0, 1. We go through all the combinations, trying not to mess it up. So there are all the combinations. All right, so what I want you to think of next is what would happen if we, say, selected this particular row and plug that into this function. So this would be a function of A, B, and C. All right, I could plug this in and I see that the value of A is 0. So this would be 0 bar, plugging into this function here. 0 bar, ANDed with C is a 1. ORed with, and then B is a 1, and C bar is a 0. All right, so we're going to work ourselves through this AND first. 1 ANDed with 0 is 0, and then we have 1 ORed with 0 is a 1, and then 0 bar is a 1, so now I'm going to have 1 ANDed with 1, and you get 1. All right, so that gives you one element of the truth table. All right, I can choose a different row. Let's choose this row. All right, so that would be f of 0, 0, 1, and we would have 0 bar for A. Let me copy the function over where you can see it. All right, so 0 bar for A, and then we have C is a 1, and then we have B is a 0, and then we would have C bar. C bar is a 0. All right, so working ourselves out through the AND first. 0 ANDed with 0 is 0. 1 ORed with 0 is 1. Okay, then we have 0 bar. 1 ANDed with 1 is 1. All right, so my point is you can go through the logic functions and figure this out by plugging things in, and it becomes pretty simple because things are either just 0 or 1. Okay, the next thing I want to talk about with the quick start is the idea that you can use truth tables to actually validate Boolean identities. Okay, so the identity I wanted to look at is A ANDed with B bar. All right, that's a function f. All right, so we could do a truth table on this. So here's A and B, 0, 0, 0, 1, 1, 0, 1, 1. Here is A ANDed with B, and then I'm gonna do this in steps, and then I'm gonna do the complement of that result. Okay, so A ANDed with B is this. You know, it's only true when both A and B are true. And then if I take the complement of that column, the previous column, this would just be 1, 1, 1, 0. All right. So now let's take a look at G. Let's say G is A bar or B bar. Okay, I can do a truth table for G. Here's A, here's B, 0, 0, 0, 1, 1, 0, 1, 1. That's all the combinations. Okay, and now what we're going to do is we're going to say, oh, what is A bar ORed with B bar? All right, so 0 ORed, if A is 0, 0, if A and B are 0, 0, then A bar is a 1, 1 ORed with anything is a 1. All right, same thing here. If A is a 0, A bar is a 1. And then for B, if B is a 0, I get a 1 also. All right, and so for this last combination, 1 bar ORed with 1 bar, that's the only time you don't get a 1. All right, so what we've noticed here is the truth table for G matches the truth table for F. All right, so that actually means that this is a Boolean identity. Okay, so A bar, B bar, A ANDed with B bar is the same thing as A bar or B bar. All right, so we've actually proven this using truth tables. This is actually De Morgan's theorem, and we're going to use this pretty early in the course. So this is one form of De Morgan's. Another form of De Morgan's is if you take A or B bar, that is the same thing as A ANDed with B bar bar. Okay, and a lot of people say break the line, change the sign. So you notice here's a bar going over both A and B. All right, so I break the line into two pieces. Here's one piece, here's the other piece, and then I change the and to a plus. All right, so I did the same thing for the second form. All right, so that's some quick start information about Boolean algebra and logic functions, and we're going to take it from there and come up with a little more systematic ways of doing truth tables. We're going to look more carefully at the properties of Boolean algebra, and we're actually going to extend logic functions to more than just and, or, and invert.